All right, welcome back from the break. And we have our last lecture for this today and for the school. There will be tutorials in the afternoon, but this is the last lecture. It's an invited guest lecture. The speaker is Andras Juhasz. He's in the math department here in Oxford. He is an expert on low-dimensional topology and also on machine learning. He was working, for example, together with DeepMind, and we are very happy to have him here. And his lecture will be on the unknotting number, hard or not diagrams, and reinforcement learning. Please go ahead.
Thank you for the invitation. It's a bit strange to be speaking on Zoom at my home institution, but it is what it is. So I've been told that Fabian talked about one application of reinforcement learning to knot theory, which was finding ribbon disks for knots. And basically the idea is whenever you have a mathematical problem that you can formulate as a game, then you can try to apply reinforcement learning to find counterexamples. And so this is another such game that where we try to use reinforcement learning to find counterexamples to some old conjecture in knot theory. I have to say in advance, we have not found a counterexample to this particular conjecture, but I will highlight some other results that we obtained along the way. So this is joint work with Mark Leckenby, who's at the Math Institute also in Oxford, and Taylor Applebaum, Sam Blackwell, Alex Davis, Thomas Eidlich, and Nenad Tomashev, Daniel Zhang, all work at DeepMind, and were involved in various aspects of the machine learning side of things. So, first of all, let me remind you that a knot is just a simple closed curve in 3 space that might be knotted. We don't look at open curves because topologically you could just retract it and unknot it that way. So we tie the 2 ends together and you get a circle, and then they can actually be knotted. And the unknotting number is a geometrically defined quantity for a knot. It's relatively easy to define, but very hard to compute, as we shall see. So the way you think about knots is you look at this projection into the plane, and there you get this curve with self-intersections, and then you record which strand is above which, and that's called the knot diagram. So given a knot K and the diagram D in the plane, then the unknotting number of the diagram is the minimal number of crossing changes required to obtain a diagram of the unknot. So at some of the crossings, you switch which strand goes over which, and you can always get a diagram of the trivial knot, which is just the standard circle in the plane up to the formation, and that is the unknotting number of the diagram. And this is always at most half the number of crossings, double points in the plane. And then you can define the unknotting number of the knot as the minimum of the unknotting numbers of all possible diagrams of this knot. And every knot has infinitely many diagrams, so this is not really a finite set, this set of numbers, and you have to take this minimum. So it's not easy to compute, and to give you some idea, there is a tabulation of knots based on minimal number of crossings in possible diagrams. And if you look at knots with at most 10 crossings, there is 165 of those. So 6 out of these have unknown unknotting number. And if you look at all prime knots with at most 12 crossings, there are 2,978 of them, and 660 have unknown unknotting number. So if you compare this with another geometrically defined quantity called the smooth 4 genus, I don't know if Fabian mentioned this, but the way you define it is you take your knot in space, which you think of as the 3-dimensional sphere, and the 3-dimensional sphere is the boundary of the 4-dimensional ball, so it's the set of vectors in R4 of norm at most 1, and you have this knot sitting on the boundary, and you look at compact oriented surfaces in the 4-dimensional ball whose boundary is this knot, and you minimize the genus of such surfaces. So the genus is just the number of holes. And this is another quantity which is hard to compute, but it is known for every at most 12 crossing knot. And so basically the class of knots that Fabian was talking about were the ones for which the 4 genus is 0. Okay. Now let's look at a concrete example. So the first knot for which the unknotting number is not equal to the unknotting number of a minimal crossing number diagram is this knot called 10-8, where 10 is the number of crossings in a minimal diagram, and it's the 8th in some tabulation of knots. So this is shown here in part A of this image. And so there are only 25 knots there is a knot table, or there's a website called Knot.info that lists all prime knots up to at most 12 crossings and various knot invariants, including the unknotting number, if it's known. And so there are only 25 knots in this knot table for which the unknotting number is known, but the unknotting number of the knot is less than the unknotting number in a minimal diagram. So usually you can compute it in a minimal diagram, but this is not the case for 10-8. And this has a unique minimal crossing number diagram, call it D, and this has unknotting number 3. So in A, you have to change at least 3 crossings to get a diagram of the trivial knot, the unknot. But actually, the unknotting number of 10-8 is 2. So let's see why that is the case. If you change the middle crossing here, in the upper left, then you get the diagram in B, and you can isotope this knot to get the diagram in C. I leave it as an exercise, and this is the knot called 6-2. It has 6 crossings, and if you change again the crossing in the middle, then that is the unknot. So you can unknot it using 2 crossing changes, but you can't do it in the minimal crossing number diagram. So this knot has unknotting number 2. And so there is a set of elementary moves on a diagram, and such that if 2 diagrams represent the same knot, if and only if you can get from one to the other using these 3 moves, these are called Reidemeister moves, and you can try to apply random Reidemeister moves to the diagram in A and find another diagram of the same knot where actually 2 crossing changes gives you the unknot. So this stochastic approach seems to work okay in this case. Now, let's look at more about the difference between the unknotting number of a knot versus unknotting number of a diagram of this knot. So Taniyama proved that if you have any knot K and a positive integer n, then there is always a diagram of this knot whose unknotting number is at least n. And it's a cute argument. What you do is you take a crossing which you have to switch in an unknotting sequence, and then you grow a finger and push it into this crossing, but you sort of knot it up. And what Taniyama proved is, you see, if you now change this crossing, which is labeled by CI, then it sort of gets linked with this finger that you pushed in. So you, in addition, have to change two neighboring crossings as well. And so the unknotting number of the diagram increases by 2 if you do this operation. And so you can push the unknotting number of the diagram arbitrarily high. Now you might have the following conjecture, and this is what Bernhard and Yablon conjectured, is that if you have a knot K, then it always has a minimal crossing number diagram D, and the crossing C in this diagram, such that if you change this crossing C, you get a knot K prime, whose unknotting number is 1 less than the unknotting number of your knot. So maybe, you can't do it in an arbitrarily minimal crossing number diagram, but there is a minimal crossing diagram such that you change a crossing and you isotope. So you move it around such that you can again decrease the unknotting number, and you continue this way, and this would give you an algorithm to compute the unknotting number. So this is what happened for 10.8 in the previous example. Unfortunately, life is not so nice, and Brittenham and Miller a few years ago found a counterexample to this conjecture. It's interesting that it's not an explicit counterexample, but what their theorem states is that there are 4 knots. It's a 13 crossing knot and 3 12 crossing knots, that each one of them you can obtain from these 13 crossing knots by changing a single crossing. And at least one of these violates the conjecture of Bernhard and Yablon. The reason why it's not explicit is because they couldn't determine the exact unknotting number of any of these knots. They just have upper bounds. So what happened is you take this 13 crossing knot, and they found a diagram, which is shown here. So this is called a braid, where you have a bunch of strands going from left to right that increase monotonically, but they might go over each other. And then you connect the rightmost ends to the leftmost ends. And so that's called the braid closure. And this is a 20 crossing diagram of this 13 crossing knot. And if you change this crossing shown in green, then you get a diagram of an 11 crossing knot that is known to have unknotting number 1. So this knot, 13 crossing knot, has unknotting number at most 2, but in the standard diagram that has only 13 crossings, you have to change 3 crossings to unknot it. So that is the key idea. And again, this shows that sometimes you really have to increase the crossing number substantially in order to find a diagram in which you can change a crossing to actually decrease the unknotting number. And I try to apply random Reidemeister moves to this 13 crossing knot in the hope of finding such a diagram, but I didn't succeed. So this kind of shows that the stochastic approach doesn't always seem to work. So more generally, you can define something called the Gordian distance. And first of all, you take the Gordian graph. This is a graph whose vertices are knots. And you connect 2 vertices, 2 knots by an edge, if they are related by a crossing change in some diagram. This is a very complicated graph, and in particular, you can define the Gordian distance of 2 knots as the distance of the knots in the Gordian graph. So in particular, the unknotting number of the knot is the distance from the unknot. And this graph is locally infinite, as for example, there is this nice result of Sebastian Bader. He showed that if you take any two knots, k and k prime, that have distance 2 in the Gordian graph, there are always infinitely many knots, k double prime, that has distance 1 from both. So here is the idea of the proof. What you do is you take two crossings that you have to change to get from k to k prime, and you can always move these next to each other. And then this picture has this twisting parameter n. So you have n full twists here and minus n full twists there. And if you change the crossing labeled A, then the positive and negative twists cancel each other. You can just untwist this whole thing and you get the knot K. And if you change B, you get the knot K prime. So these are knots that lie at distance 1 from both K and K prime. And you can use a certain knot invariant called the Alexander polynomial to show these are distinct for distinct n. Right, so how do you compute the unknotting number? First of all, how about computing just the unknotting number of a fixed diagram? Well, this is sort of exponential in the number of crossings, because you have to, in principle, check all subsets of crossings up to the number of crossings over 2. And that's exponential. So in practice, even computing this is not so easy. And this is the quantity that we trained a reinforcement learning agent to get upper bounds on. And there is no algorithm known to compute the unknotting number of a knot. There was this Bernhardt-Diablan conjecture, but since that fell, there isn't even a conjectural algorithm. However, in practice, you can often get a good upper bound using the following heuristic. You take your knot, you change a crossing such that the crossing number becomes minimal after simplifying, and you repeat this process. So I mentioned the 4-ball genus of a knot, this G4K, which is the minimal genus of a compact oriented surface in the 4-ball whose boundary is your given knot. And it's a very nice argument to show that this is less than or equal to the unknotting number. And there are several invariants that are both computable and give lower bounds on the 4-ball genus. And the classical one is the knot signature, sigma of k. And then there is an invariant, which is the Rasmussen S invariant, obtained using Kovanov homology, that is related to representation theory and TQFTs. And then there is the Ozsváth-Szabó Tau invariant and new invariant, which is defined using Hagar-Floer homology, which are quite sophisticated knot invariants. But these are computable and give lower bounds on the 4 genus. However, there are basically no invariants that we know that give a lower bound on the unknotting number that doesn't give also a lower bound on the 4 genus. And the thing is that the difference between the 4 genus and the unknotting number can be arbitrarily large. So this is one of the big difficulties, finding good enough lower bounds on the unknotting number. And in fact, there are very few infinite classes of knots for which we explicitly know the value of the unknotting number. We know it if we have an upper bound and a lower bound that agree. And there is the class of torus knots. These are just knots that you can draw on the surface of a torus, and the PQ torus knot winds P times in the longitude direction and q times around the meridian direction. And this has unknotting number p minus 1 times q minus 1 over 2. So the unknotting number is easy to define, and it goes back to the beginnings of knot theory, and the following conjecture also is a classical one that's been around for at least, I don't know, 50, 60 years, if not more. So if you have two knots, there is an operation called the connected sum, which you obtain by taking two diagrams of your two knots, k and k prime. You draw that next to each other. Then you delete two segments of this diagram and connect them by arcs. And conjecture is that the unknotting number is additive under connected sum. So this is the conjecture that we were trying to find counterexamples to. And the best known result is due to Martin Charlemagne from the early 80s. And it says that if you take two non-trivial knots, U is the unknot, then the unknotting number of their connected sum is at least 2. To give you a sense of how weak this is if you have, say, k and k prime both have unknotting number 1,000,000, then you know that their connected sum will be at least 2. You don't even know that it's at least the unknotting number of one of the sum ends. Now, in certain cases where one of the sum ends is of special form, for example, a PQ torus knot, there is this relatively recent result of Alishahi and Eftekhari. It shows that the unknotting number of such a connected sum is at least p minus 1 if p is less than q. And this was proved using Hegar-Fleur homology. Now, in certain cases, you do automatically get additivity of the unknotting number. For example, if both sum ends have signatures with the same sign, and the signatures give sharp lower bounds on the unknotting number, then since the signature is additive under connected sum, so will be the unknotting number. So if you want to find a counterexample to this, then you better consider knots whose signatures have the same sign. Opposite signs. And so the first such case where we don't know the answer is if you take the 2-3 torus knot as the first non-trivial knot, has 3 crossings, and the mirror of the 2-5 torus knot, we don't know the unknotting number of this. And this is just a knot with 8 crossings. So this is probably the smallest knot for which the unknotting number is unknown. Now, there is a more intrinsic 3-dimensional way to imagine the unknotting number. So a crossing change, instead of looking at diagrams, you can take an arc embedded in 3 space whose endpoints lie on your knot and whose interior is disjoint from the knot, and then this is oriented, and then you perform sort of deformation of one of the arcs. You push it up along this arc until it crosses the other one. So this is the same as a crossing change if you look at the knot so that this red crossing arc becomes vertical, then this becomes a crossing, and this is just a crossing change. And then the unknotting number is the minimal number of crossing arcs required to unknot your knot. And you might wonder whether it's the case that if you have a collection of crossing arcs that unknot a connected sum, is it true that you can always move one of these arcs into one of the sum ends? And if this were true, then this would give you a proof of the additivity of the unknotting number, because you're always changing a crossing in one of the two summands. So you need at least the unknotting numbers of the two summands to unknot your knot. By the way, if anyone has any questions, then feel free to ask. Now, since this is a machine learning conference,
there's a question.
Okay.
I have a basic confusion about the conjecture.
Yes.
So if you take the connected sum of two knots for which you know the unknotting number.
Yep.
And let's say that the second one you arrange it such that the crossings are the opposite from the other one. Shouldn't, when you put them together, don't these crossings just undo each other, and you would obtain the unknot?
So what do you mean by opposite to each other?
Like if you have, like you have one strand above the other one, or the second one above the first one.
So they don't undo each other.
If you take the braid representation, yep, and you have the inverses, basically.
Well, I mean, then you would be taking the same knot, you mean?
Yeah, the same knot.
The knot and its mirror. Yeah, that's not true, because you see these crossings don't lie next to each other. And also, you are composing the braids. That is not the connected sum. That's, I think, yeah, maybe that is where your confusion
comes. You take them in opposite order. So I guess this is a mirror.
Yeah, it doesn't work. But I think what you're thinking about is taking the product of the two braids. But the closure of that is indeed the unknot, but that is not the connected sum of the two knots. It's known that that's a non-trivial knot, because there is the three-dimensional genus, which is additive under connected sum. Yeah. But it's a bit hard without drawing. I'll be back in Oxford next week, so if anyone wants to catch me and ask questions, then I can explain in person.
Can I also ask a question?
Yeah, of course.
Can you go back to the previous slide?
Yes.
Yeah, so another way of constructing a potential convex, so a case where you don't know whether this conjecture is true is you could take knots where the signature is the same sign, but the lower bound is not saturated, right? So yeah, where UK is not equal to sigma of K, or not known to be equal.
Yeah, so the problem is you could, in principle, yes, but how do you sort of need to know the unknotting numbers of the two summands to be able to say that this is a counterexample. And the way you know that unknotting number is that one of these invariants will give you a sharp lower bound. And unfortunately, these invariants will typically be additive under connected sums. So yeah, I mean, then that invariance should have different signs for the two summands.
Okay, but so of this 8 crossing knot that you're writing down as the sum of the 2 torus knots, this is the smallest one for which it's unknown.
Yes, to my knowledge, yes.
Thank you.
Okay, so here is some quick background on machine learning, mostly for mathematicians and probably not so new for people in this workshop. But so there are different machine learning paradigms. One is supervised learning, where you're trying to predict some labels from in a labeled data set, which is basically learning a function in order to minimize an error, maybe an L2 norm. And this can be either a classification problem, like a spam filter, or a regression, for which the simplest example would be linear regression. And so as everyone knows, the real breakthrough came with increasing computing power that enabled the training of artificial neural networks, which from my point of view are just composition of affine maps and some nonlinearities, and you train these using stochastic gradient descent. And then another machine learning paradigm, which is the one we use here, is reinforcement learning, where some agent, which is computer code in this case, learns to perform some actions to maximize a reward. So this could be a game like chess or Go, or it could be a self-driving car or a robot. And this can be phrased as a Markov decision problem, which I quickly review here. So this is a four-tuple SA, PA, and RA, where S is a set of states, and in our case, states are diagrams of a given knot. Okay. Now, given a state S, so a knot diagram, you have a set of actions A of S. These are the actions are changing one of the crossings in this diagram. And in the general setup of Markov decision problems, you have a probability that if you perform action A in state S, you get to another state S prime. That here it's 0 or 1, because this is completely deterministic whether a crossing change leads from one knot to the other. And finally, but very importantly, we need a reward function which gives you the reward of performing action A in state S and reaching state S prime. So the reward functions that we used was one for reaching a diagram of the unknot and 0 otherwise. Initially, we tried reward 0 for reaching the unknot and the punishment of -1 otherwise, but this seemed to work less well. And so what we need is a policy pi, and this is a potentially probabilistic mapping from states to action, which tells you, which action to take in a given state. And our objective is to choose a policy that maximizes, for example, the state value function, v pi of S, which is the expected cumulative discounted reward. So you start in state S, which I label as 0, and then you apply the policy multiple times, you get into states S1, S2, and so on. And you choose a discount factor gamma between 0 and 1, and you add up all the rewards that you encounter along the way, but each time you discount using this factor gamma. So if it's 0, then the agent only sees the immediate reward, and as you increase it, it will care more and more about future rewards down the line. And one of the most classical ways to do this is Q-learning. This is not what we use, but it's easier to explain. So in this case, the goal is to learn a state action value instead of just a state value function. This is Q, where Q stands for quality. So Q of a state and an action gives you the expected discounted reward if an action A is taken in a given state S. And so at time t, your agent selects an action AT, then observes some reward RT and enters the next state ST plus 1. Then you somehow initialize Q, and then this is updated using the Bellman equation, which is the new Q at STAT is the old Q, plus alpha times, where alpha between 0 and 1 is the learning weight, which corresponds to the step size in stochastic gradient descent, and times so you take the reward, and then you take the discount factor times the maximum of the Q's, this expected reward you can get from ST plus 1, and then you subtract off the old Q value. Right. And then you repeat this iteratively, and you hope that this will converge to the real Q. And as usual, there is this dichotomy between exploration versus exploitation. So whether when training or reinforcement learning, we use the learned policy, that's exploitation, or we explore new possible actions. And one solution to that is to use an epsilon greedy policy. So you take some small positive epsilon, and with probability epsilon, you choose a random action, so you explore, and with probability 1 minus epsilon, you perform the action, an action AT that maximizes the expected cumulative discounted reward. And then you can combine this with neural nets, and so you can encode this Q function using a neural net, which is just a function for R to the states to R to the actions. And if ES is the basis vector corresponding to state S, you apply your function F, your neural net, and you take the coordinate corresponding to action A that will give you Q of SA. And you update this using the learning process, using the Bellman equations. Now, the agent that we actually used most was Impala, which stands for Importance-Weighted Actor-Learner Architecture. And this is a distributed agent, which is ideal for parallelization. In this case, you have one or more learners and multiple actors that explore the state space. So you are learning a policy pi and a value function v pi via stochastic gradient ascent. And your set of actors repeatedly generate trajectories of experience. So in this case, they try to unknot knots. And you have one or more learners that want to learn the policy based on this experience that is always communicated well in batches with the learners. The complication comes from the fact that the policy of the actors always lags behind the learner's policy. So there is some mathematical trickery to compensate for that. Now, another machine learning approach that we explored was imitation learning. And in this case, you have an agent that tries to learn a policy that mimics some expert behavior. So this is the way, say, a child learns from adults. We don't have a reward function. And the simplest version, which we used, was behavioral cloning. So using supervised learning, one maps environment observations to ideally optimal actions taken by some expert. There are more sophisticated approaches to this called, for example, adversarial imitation, where you can view this as a minimax game between two AI models. So this is an instance of generative adversarial nets, where you have an agent policy model that will produce actions, and it wants to attain the highest reward from another agent, the reward model, using reinforcement learning. And the reward indicates how close to this expert-like action the taken action is. And so by iterating this, the agent policy model will hopefully converge to one that always produces expert-like behavior. So let's talk about supervised learning and unknotting. First, we just trained a random forest classifier and also neural net to predict the unknotting number from some knot invariants. And we use the Alexander polynomial, the Jones polynomial. So these are polynomial invariants, the Rife, which is the sum of crossing signs. You can always associate a plus or minus sign to each crossing, and something called the longitudinal translation, which is defined for knots whose complement admit a hyperbolic structure, which is often the case. This is called the longitudinal translation. So we had about 10,000 random knot diagrams, which we generated using a software called Snappy. These were between 3 and 25 crossings, and the agent had accuracy 80% compared to a naive baseline of 50%, where you predict the most commonly occurring value of the unknotting number. Now, if you look at a given diagram, in some diagrams, every crossing is in a set of in a minimal unknotting set. In others, only a small percentage will be. And this might be kind of counterintuitive, but this is the case. And so we trained a supervised learning agent to predict whether a given crossing is in an unknotting set. And for this, we had about 100,000 random diagrams between 11 and 30 crossings. And this achieved 85% accuracy compared to a naive baseline of 50%. So this will pick out a crossing that will be in a minimal unknotting set. And so one can...
Can I ask a question?
Yes.
So how did you encode the crossing in the, I mean, the input you said is the Alexander, the Jones polynomial. So how do you decode this into a crossing?
Well, no, this was in the environment. The agent, agent only saw the invariants.
And what in its output is a crossing. So how does this work?
Well, I mean, so we generated, so what we did was we brute forced unknotting trajectories for diagrams and use behavioral cloning to pick which crossing to take. So it was trained on these subsets of crossings.
Oh, okay. Yeah, thank you.
So this was an instance of imitation learning. The reason why we started with supervised learning is we wanted to figure out which knot invariants are most useful for predicting the unknotting number. And so which invariants to use as features for reinforcement learning. So this is a very, this kind of useful advice when you want to do reinforcement learning is maybe start with supervised learning because that's much easier and see what is useful and what's not. Right, so let's move on to reinforcement learning. As I mentioned before, our goal was to train an RL agent that performs crossing changes in a fixed diagram to unknotted, and this way obtain upper bounds on the unknotting number. And we mostly use this Impala agent. We tried other ones as well, but this is what we spent most time with. And this could determine the unknotting number with fairly high accuracy up to about 200 crossings. And that is well beyond the range of brute forcing. So, you know, if you might be disappointed that this is a finite problem, that you just compute the unknotting number of a diagram. But if you think about chess and Go, those are also finite games, and it's not feasible to brute force them. So the fact that machine learning could learn this is kind of remarkable. Now let's look at the representation. So since knot diagrams are hard to feed into a neural net, we used invariants of a diagram, and we also used invariants of all possible diagrams that you can obtain using one crossing change. And so what features did we use, which invariants? We used the Alexander and Jones polynomials. And it's not completely clear what's the best way to feed polynomials into a neural net. What we use the coefficients, certain evaluations of these polynomials, including evaluations of the first three derivatives, and minimal and maximal degrees. And we also tried larger sets of invariants, but these two give almost the same accuracy as larger sets of features. Now, the issue with many of the other invariants is that they are either fail to compute for large knots, for a significant percentage, maybe at least 20%, and then it's not so useful for machine learning, or they are very slow to compute for 100, 200 crossing knots, and one of these is knot-Floer homology. So we mostly used software called Snappy that computed these invariants. Another piece of advice is it's much easier if there are existing tool sets for computing the mathematical objects you want to work with when starting such a reinforcement learning project. Another feature that was particularly useful was the sum of absolute values of the coefficients of the Alexander polynomial that improved the performance. And if we use both the Jones and the Alexander polynomial, that performed much better than only the Alexander polynomial. And in fact, usually the Jones polynomial performs better than the Alexander polynomial, but not always. The issue is that the Jones polynomial is kind of hard to compute. It's exponential time in the crossing number, and Alexander polynomial is much faster to compute. So we were tempted to just use the Alexander polynomial, but didn't get as good a performance. So one of the reasons why this might be the case is that the Jones polynomial is conjectured to detect the unknot where the Alexander polynomial doesn't. And as I mentioned, our agent architecture used this thing called one-step look-ahead, where the agent computed the Alexander and Jones polynomials of all knots that you can obtain by changing one crossing. So that meant that the environment was really slow and required a lot of compute. And one of the conclusions I think that one can obtain from this is that the Jones polynomial seems to contain some yet unobserved unknotting information. So I mentioned braids briefly, and we also experimented with agents that represent knots as braids. For the following reasons, the Jones polynomial can be computed in polynomial time if you fix the braid index, which is the number of strands going from left to right. Also, there are nice inequalities, strong inequalities on the unknotting number called the Slice-Banachine inequalities. Here, beta is a braid and beta cap is the braid closure. So we connect the strands on the right to the strands on the left. And W is the width of the braid, and N is the number of strands of the braid index, and C is the crossing number. And another motivation for using braids was that if you take a connected sum, then by inserting braid words that represent the identity and gives you pretty good mixing between the two components. So here in the top, you have a connected sum of two braids, and we inserted some trivial braid words, and the red crossings are crossings between the two components. So if you want to find a counterexample to the additivity of the unknotting number, you have to change crossings between the two components. And we trained an Impala agent that performed pretty well. We also experimented a little bit with transformers, which seemed to work okay, but didn't generalize very well as the crossing number increased. But this is probably because we didn't try very hard. So trying transformers is probably a good idea. Now let's get back to our main goal, looking at the additivity of the unknotting number and reinforcement learning. So what was our data set? We obtained the unknotting number of 31,000 random knots between 10 and 60 crossings, 26,000 so-called quasi-positive knots between 10 and 50 crossings, and we made sure that this had relatively large signatures. And for these knots, the upper bounds on the unknotting number obtained using the reinforcement learning agent agreed with the lower bounds from knot floor homology. So this invariance tau and nu that I mentioned before. So we knew the exact unknotting numbers, and these will be summands when taking connected sums. So we searched for potential counterexamples to the additivity of the unknotting number by taking connected sums of knots and then overlaying the two summands, just putting them on top of each other. And in some cases, that was about 100,000 cases, in addition, we mixed up these overlay diagrams using random Reidemeister moves. So this is in spirit of the stochasticity that I mentioned earlier. Now, unfortunately, we couldn't perform too much mixing because the limit of our unknotting agent was 200 crossings. And so in the end, our summands were either at most 12 crossing knots from knotinfo with known unknotting number, torus knots, for which we know the unknotting number, or one of the above 57,000 knots with known unknotting number. Right. And we have not found a counterexample to this conjecture. Now, it's not clear how to interpret this, whether it means that this is some sort of evidence for the verity of the conjecture, or our reinforcement learning was not good enough, although it seemed to perform reasonably well. Or it's possible that if there is a counterexample, you have to increase the crossing number by a lot, and that's just beyond the range of the reinforcement learning agent. But maybe you can view it as some sort of weak evidence that this conjecture might actually be true. So remember, there was this stronger conjecture which says that in every collection of unknotting arcs for a connected sum, there is always one that you can isotope or move into one of the summands. So we call a crossing change intercomponent if it really lies between the two summands. So if you change that crossing, you no longer have a connected sum. And you can verify this, for example, by saying that this is a hyperbolic knot, which means that the complement admits a hyperbolic metric. And it was somewhat surprising and interesting that the agent performed a number of intercomponent crossing changes. So it didn't just do crossing changes in one of the summands and then in the other, but it started changing crossings between the two summands and found minimal unknotting trajectories. And using these, we could construct counterexamples to the stronger conjecture by undoing the crossing changes that lay in one of the two summands. So here is an example of that. This is a diagram of the two summands thrown in two shades of blue. And this can be annotated by changing the four red crossings that are between the blue, dark blue, and sort of cyan or turquoise or whatever summand. And if you change any one of these, you no longer have a connected sum. So this is a counterexample to the strong conjecture. And by thinking a bit harder about what happens here, we managed to prove a theorem. So if you have two prime knots, K1 and K2, that are not two bridge knots, that's just a not very restrictive technical condition that is probably not necessary, then there is always a diagram of the connected sum and a set C of unknotting crossings whose size is the sum of the unknotting numbers of the two summands, such that if you change any crossing in C, you result in a prime knot. So in fact, basically for any connected sum, you can find such a diagram that you can unknot it using intercomponent crossing changes only. And maybe due to the interest of time, I'm gonna skip this slide and talk about hard unknot diagrams. So we say that a diagram of the unknot is hard if in any sequence of Reidemeister moves to the trivial diagram, you first need to increase the unknotting, the crossing number before you can decrease it. And it's kind of surprising that there are such diagrams, and here is a picture of such a diagram. So in order to simplify or unknot this diagram, you first have to increase the number of crossings before you can decrease. And previously, there were not very many such examples in the literature. There was a paper that was published this year, and that collects all known examples from the literature that had 11 hard unknot diagrams and 2 very special infinite families. And initially, when we started doing machine learning and knot theory, we tried to use generative adversarial nets, so a setter and a solver, to construct such hard unknot diagrams by one agent trying to make your diagram more complicated such that the other agent, which was trying to unknot it, couldn't unknot. But we didn't get any interesting hard unknot diagrams out of that. However, while running this unknotting agent, we found about 5.9 million unknot diagrams that this software Snappy couldn't simplify. That has different heuristics, and this was this level heuristic, it doesn't matter really. And we've checked that out of these 5.9 million, most of these diagrams have at most 35 crossings. About 2.5 million are in fact hard, and no two are related by this third Reidemeister move. So they are essentially different diagrams. So that's compared to the 11 existing previously, plus these 2 special infinite families, now we have 2.5 million. And many of these survive a much more thorough heuristic, unknotting heuristic of Snappy called global. And the reason why these hard unknot diagrams are interesting is because they provide potential counterexamples to unknotting algorithms. So there are algorithms known for unknotting a knot, but the big conjecture in computational knot theory is whether there is a polynomial time unknot detection algorithm. So this is what I had in mind. And here is a picture of one of these 2.5 million hard unknot diagrams. This has 42 crossings and is kind of flexible in some sense. You can try to unknot it yourself if you have time. All right, thank you.
Thank you very much. Are there questions? Can I ask a question?
Of course.
So for the unknotting, you also use the same inputs. So you also use the Jones and the Alexander polynomial, and then you did this one step.
Look ahead, yes.
Yeah.
I mean, there were agents we tried agents that only use Alexander. That's much faster to train because the Alexander polynomial you can compute in polynomial time, and we tried with both Alexander and Jones, and only Jones, and we have comparisons of efficiency of these different agents.
And in order to answer the question of what the Jones polynomial encodes about unknotting that made it more feasible to use for finding bounds on the unknotting number, are you planning on studying, I don't know, rollouts of agents and trying to see what it potentially picked up, or look at, I don't know, homologies of these and try to understand what it is that the Jones polynomial encodes, or you just leave it at the level of an observation?
I think we'll leave it as a level of observation, but definitely there seems to be something that that hasn't been observed, but I don't know how to interpret these results very well.
Yeah. Okay.
When you did the unknotting,
Yes.
What was your sample of knots? Did you choose many of these hard knots, or it was?
So I talked about the data set. We generated random knot diagrams using.
If you were to do the training with including more of these hard knots, do you think it would behave differently?
Maybe, I don't know. I mean, these are the problem is you don't need, these are already unknots, so you don't have to unknot them.
Sure.
The Jones polynomial is trivial, and it will just, we compute it and we'll say that you are done. So that I don't think it will change anything. I mean, that's of course a conjecture that the Jones polynomial is one if and only if your knot is the unknot. But there are other computable invariants. Not Fleur homology can detect whether or not is an unknot. So yeah, I mean the agent, since it only doesn't see the knot, it seems the invariant, it will immediately think it's dealing with the unknot. Does that answer your question?
All right, I don't see any further questions. So let's thank the speaker again. Also, this was the last lecture in this lecture series. Of course, there are tutorials, but I think we can all agree that this is a phenomenal school and we all learned very much. I at least learned a lot. So I think we should take the opportunity and thank the organizers and everyone behind the school. So especially Andre and Yang, who not here, I think.
Yeah, Yang is coming, yes.
Okay. And of course, also the helpers, Michelle and Lucas and Kit and Thomas, and did I forget someone? Okay, yeah. Thank you very much. It's been great.